Hello, this is Ryan Woodward recording for milestone 6 of the Poor Man's ALU. And I am very excited to discuss this. This has been a very fun project for this semester. Lots involved. Spent a lot of time learning so many different things. It has been such a fantastic couple semesters in the embedded systems classes. I am really going to miss being able to work with this board more regularly than I would like. But let's get into the milestone and talk about this Poor Man's ALU project. Just briefly, I will discuss the project introduction and its objectives. I will share a little bit about the embedded application and the functionality. I'll discuss the technology and my implementation approach. I'll share some technical design decisions, and then I will provide a brief demonstration, and then I will conclude the presentation there. So regarding the project itself, it's an embedded systems application built for the DE10 standard board that involves a C application and VHDL and Verilog circuits, but mostly VHDL. I focused on building that out, and Verilog was a secondary goal of mine to build it using Verilog. But the project itself is a simplified arithmetic logic unit, hence the name Poor Man's ALU. I loved when we called it that, probably week 3 or week 4 in the semester perhaps, and I just ran with it because I loved the name. It just was humorous, and so I went with it. But the arithmetic logic unit can support operations between two 4-bit numbers. It can do addition and subtraction, and it can do a Boolean logic AND of those two 4-bit numbers. For the overall project, it has a C program, and that also includes some ARM assembly, some inline ARM assembly in there. And that C program interacts with the GPIO pin, which is used to communicate the data of the C application, namely the two 4-bit numbers, to the FPGA and the circuits there, and eventually onto other peripherals. So regarding specific functionality, it begins with user input at the terminal side, where we run the C program, and the user can enter two 4-bit numbers in decimal format, but can you enter those numbers into the terminal, and by executing that, it will be passed on to the FPGA there. And on the board, once those two values have been passed, the default operation will be addition, and you'll see that right away. If you were to enter 5 and 4, as I'll show in the demo, you'll see 9 be passed immediately to the hex display, and that lets us know that addition was successfully performed. But if we were to flip switch 0, then the operation would be subtraction, and then in the case of the 5 and 4 being passed, we'd see a 1 on the hex display. And then if we were to flip switch 1 instead of switch 0, we would actually be toggling, or not toggling, but selecting the output of the multiplexer. That quad 2-to-1 multiplexer is a circuit in the project that will pass one of the 4-bit inputs to the output. And if we flip it, it will go from the arithmetic unit being displayed to the Boolean logic unit being displayed. And that's where that output selection happens. But all the peripherals involved in this project are two 7-segment displays for the final output, the results of the operations. We have an LED involved to display that there was a carry or borrow out of the arithmetic unit. It glows often during the AND or the Boolean logic result, but it's irrelevant for that. We have two switches involved, and then finally we have a GPIO pin as an input. So this is the system diagram, just continuing on with project overview. As we can see on the left, we have our C program on the ARM processor on the HPS side of the board. And then on the right, we have the FPGA, where the remainder of the circuits and the peripherals are found. We see that from the GPIO pins, we have two 4-bit inputs going into the ALU circuit, and those eventually are passed to the Boolean logic unit and the arithmetic unit. Both of them are. We can see on the bottom left corner that there are two slide switches. One will be used as actually the carry in for the arithmetic logic unit, but it is actually used to determine which operation, addition or subtraction, is performed as well. And then the second switch will go to the multiplexer, And even though there's an enable there, I've actually disabled that function. I basically set that enable switch to 0, or I didn't assign it a pin when I was working, actually building out the project, because I did not need an enable switch. If we're at high, all the outputs would be 0, and I didn't need that. So I decided not to actually assign the pin to the enable, but I still had it built into some of the circuits anyway. You'll see the LED for our carry out and borrow out from the arithmetic unit, and in the top right you'll see our BCD decoder, which was originally supported up to 0 to 9 for the hex display, but now it supports 2 7-segment displays, that being 0 to 15. Moving on, we have the technologies that were leveraged for this project. The C programming language and ARM assembly language were used for the HPS side of the project, and on the FPGA side I used Quartus to perform functional simulations and waveform simulations, and that's where I actually coded in VHDL and Verilog. And this is all built on the DE10 standard board, and on that board we have Lenaro Linux, which is on a little chip that connects to that board. And some technical design decisions, beginning with the hardware selection. I didn't really know, admittedly, what project I was going to do this semester. I thought of some ideas, but when we came up with the ALU, that seemed like a perfect route to be able to explore a variety of concepts and topics related to digital logic design, RTL, embedded systems, and so on. And I wanted to learn as much as I could, and that seemed like the perfect avenue for me to do that, because a lot of the nitty-gritty things seem to be omitted sometimes with a lot of tutorials online, such as K-maps, Boolean logic, and truth tables. We don't see those quite as much as I think we should, but those were excellent for this in regards to this project for me to learn and actually implement quickly and learn those pretty good. But back to the peripherals, I needed to select what peripherals I would need, and I wanted to have a display, but I also wanted to have the inputs where I could select with switches. And after I discovered what circuits I would probably need to actually do some of the operations, the addition was intuitively going to be a full adder, and then I discovered a full adder subtractor circuit, so that allowed me to easily support subtraction. And then doing an AND, a Boolean logic AND or circuit was easy. I probably could have done an OR circuit for this and just added that in. It probably would have been quite simple to actually add that in. But aside that, I needed a way for the C program to communicate with the FPGA, and that was intuitively going to be the GPIO pins. That's probably the easiest way to do it, and so I elected to use those. And the LEDs were kind of the last ditch thing, because I needed some extra output peripheral, and it was simple enough to actually add an LED to serve as the carry out or borrow out for showing that our operation produced a number greater than 16 or less than, well, not less than, but it will show that something came out that the number displayed does not contain. Regarding software architecture, and I probably should have a better note for this, but I wanted to really focus on the quality of my code. I wanted to modularize and abstract it out really well. And I think that's really demonstrated pretty well, in my opinion, of the C program. We can see that from the main application interface with that main function, it's like 2 or 3 layers above where we actually see the hardware that we'd begin working with. It's like the write to parallel port is a couple files away from that main application file, and that's the kind of quality I wanted to get when we modularized it like that. We have a main function, an ALU module, a hardware module, and even a register file for actually interacting with that JP1 port. Another point I want to add onto this is the variety of architecture models for RTLs. So data flow models, behavioral models, and structural models. I implemented all 3 at some point during this project. And even though I think for the final project I leveraged structural most, I implemented data flow and behavioral for the entire project. All 3 were used in the final product And that was kind of the idea, is that this final project would contain a lot of different things that I got to experiment with. It has C, it has assembly, it has VHDL, it has Verilog, it has behavioral, structural, and data flow modeling, and there's K-maps, there's Boolean logic, there's digital logic design, there's diagramming, all sorts of concepts that I needed to learn, that were very important for me to learn. I got to dabble in them a bit. And another final portion of this, when it regards to a design decision, is to actually, one, focus on design itself, design and plan from the very beginning, spend an exorbitant amount of hours planning and designing the requirements, laying those out clearly, and then having a breeze of a time to just develop. I spent far more time planning and designing, doing K-maps and truth tables, and researching circuits and researching actual ALUs to determine what I would need for this project. And that turned into a very easy development stage. And in fact, aside actually having the C application communicate with the FPGA, which was a very small change that we had to make in class that one day, probably 2 months ago, I was prepared to call this project at least complete, in the sense that I had all the circuits and the code necessary to do the basic ALU functions, addition, subtraction, and the Boolean AND. That was probably at the latest done halfway through the semester. And that's that emphasis on engineering, the engineering mindset, but the emphasis on design and requirement gathering that my professors had really tried to instill in us. But another aspect of that is testing. To get to my final third point, there was so much testing involved to verify each circuit, to verify each component of code, and not only was it done in, say, waveforms and simulations, but I also would make basic circuits and port that over to the FPGA and test them individually, piece by piece, so that it would all work seamlessly together. Alright, so I will go through a brief demonstration of the code. There will be some commentary, but I'll provide that rather than having captions in another video that you can find on my YouTube, but I will have that here. And for this first portion, if we were to type in the numbers 5 and 4, enter those into the terminal, then we would have the value 9 be printed out to our hex display, as you'll see here in a moment. Now, by default, that switch on the very end on the right is low, and that means the operation is addition. But as I flipped it high, we saw that it was subtracting, 5 from 4 being 1, and that second switch went high for us to AND those two values. And obviously 5 and 4 share that 1 in the 4's place, and so that's why we see 4 to the output. Now, if we were to enter, say, 6 and 9, we would see 15, which is actually the greatest number we can display on the two hex displays, because that's the largest 4-bit number, and we would see the same results. 9 minus 6 is 3, and then if we were to AND those, we would actually see 0, because none of the values in the binary value of 6 or 9 are shared, and because there are no ones that are shared, we see only 0. And I will briefly just want to point out that LED, we don't see it because there's no carryout. 9 plus 6 is 15, but we would see that go high if it were to say, let's say 9 plus 7, it would be 15 displayed, but we'd see an LED go high. All right, and that is it for the poor man's ALU.